The setup has a few potential issues. Let's address overcurrent protection. The 40 amp main breaker is rated for 40 amps of continuous current. Each 32 amp contactor has a rating of 32 amps. Each of the 9 motors, each rated at 1 horsepower and 480 volts, consumes approximately 1.5 amps each. The total calculated load on each contactor is 9 times 1.5 amps, which equals 13.5 amps. The total load in the main breaker is well below its 40 amp rating, which seems adequate. However, it is important to consider the surge current during motor starting. Now, let's discuss branch conductors. The parallel number 8 THHN wires from the main breaker to the contactors are likely inadequate. The National Electrical Code, or NEC, requires that branch circuit conductors be sized for the maximum load that they will carry. In this case, each contactor has a rating of 32 amps, so the branch conductors should be at least number 8 American wire gauge, or AUG. Now, let's cover tap conductors. The number 10 THHN taps from the number 8 branch conductors to each contactor are also undersized. The National Electrical Code, or NEC, generally requires that tap conductors be at least the same size as the branch circuit conductors. Here is a suggested revised setup to address these issues. Firstly, use a 60 amp main breaker. Secondly, run number 8 THHN branch circuit conductors from the main breaker to each contactor. No tap conductors are necessary. Each contactor would be directly connected to the branch circuit conductor. This revised setup would provide adequate overcurrent protection and ensure that the conductors are sized appropriately for the load. To understand conductor sizing, consider these key factors. Firstly, ampacity. Ampacity is the current in amps a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The National Electrical Code, or NEC, tables such as Table 310.15b16 provide ampacities for various conductors based on insulation type and installation conditions. Secondly, correction factors. Correction factors are applied to the ampacity of a conductor when the ambient temperature is higher than 30 degrees Celsius, which is 86 degrees Fahrenheit, or when there are more than 3 current-carrying conductors in a raceway or cable. These factors reduce the allowable ampacity. Thirdly, termination temperature. Equipment terminals are often rated for 60 degrees Celsius or 75 degrees Celsius. Conductors must be sized based on the lowest temperature rating of any connected terminal. For example, if a terminal is rated for 75 degrees Celsius, you must use the 75 degrees Celsius ampacity column in Table 310.15b16 of the National Electrical Code, or NEC, even if the conductor insulation is rated for 90 degrees Celsius. Fourthly, motor full load amps, or FLA. Determine the motor's full load ampacity, or FLA, from National Electrical Code, on NEC Tables 430.248, 430.249, and 430.250. These tables provide the full load ampacity, or FLA, values for motors based on horsepower, voltage, and phase. For a 1 horsepower, 480 volt, 3-phase motor, the full load ampacity, or FLA, is approximately 1.56 amps according to Table 430.250. Fifthly, motor branch circuit sizing. The National Electrical Code, or NEC, Section 430.22 requires that branch circuit conductors supplying a single motor have an ampacity of not less than 125% of the motor's full load ampacity, or FLA. This accounts for the motor's continuous duty and potential overload. Therefore, the minimum ampacity for the branch circuit conductors is 1.25 times 1.56 amps, which equals 1.95 amps. Sixthly, motor overload protection. Motor overload protection is intended to protect the motor controller apparatus, and motor branch circuit conductors against excessive heating due to motor overloads and failure to start. Overload protection devices are typically sized at 125% of the motor's full load ampacity, or FLA, for standard motors, but can be higher for certain types of motors or applications as specified in the National Electrical Code, or NEC. Seventhly, short circuit and ground fault protection. Short circuits and ground fault protection protects the motor branch circuit conductors, control apparatus, and the motor itself against short circuits or ground faults. This protection is typically provided by fuses or circuit breakers. The National Electrical Code, or NEC, Section 430.52 provides guidelines for selecting the maximum rating or setting of the overcurrent protective device for motor circuits. Eighthly, conductor ampacity adjustments. After determining the initial ampacity of the conductors, it's important to adjust for ambient temperature and the number of conductors in a raceway, cable, or bundle. When conductors are installed in environments with high ambient temperatures or when multiple current-carrying conductors are bundled together, their ampacity must be reduced to prevent overheating. Ninthly, voltage drop. Voltage drop is the decrease in voltage along a conductor from the source to the load. Excessive voltage drop can cause equipment to operate inefficiently or fail prematurely. The National Electrical Code, or NEC, recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Tenthly, grounding and bonding. Grounding and bonding ensure a low impedance path for fault current, which helps to protect personnel and equipment from electrical shock and fire hazards. The equipment grounding conductor, or EC, must be sized according to the National Electrical Code, or NEC, Table 250.122 based on the rating of the overcurrent protective device in the circuit. Considering all these factors is crucial for a safe and compliant installation. Now let's delve deeper into the specific National Electrical Code, or NEC, articles and sections that are relevant to the scenario. Firstly, National Electrical Code, or NEC, Article 430 Motors, motor circuits, and controllers. This article provides comprehensive requirements for motors, motor circuits, and motor controllers, including conductor sizing, overcurrent protection, control circuits, and motor control centers. It is the primary reference for ensuring compliance with motor installations. Secondly, National Electrical Code, or NEC, Section 430.22 Single Motor. This section specifies the minimum ampacity requirements for branch circuit conductors supplying a single motor. As mentioned earlier, the conductors must have an ampacity of not less than 125% of the motor's full load ampacity, or FLA, as determined by National Electrical Code, or NEC, Tables 430.248, 430.249, and 430.250. Thirdly, National Electrical Code, or NEC, Section 430.52 Motor Short Circuit, Ground Fault, and Overload Protection. This section provides guidance on selecting the appropriate overcurrent protective devices for motor circuits. It specifies the maximum rating or setting of the short circuit and ground fault protective devices, such as fuses or circuit breakers, based on the motor's full load ampacity, or FLA, and the type of motor. Fourthly, National Electrical Code, or NEC, Section 310.15 Ampacities for conductors rated 0-2000 volts. This section contains tables that provide the ampacities of conductors based on their insulation type, size, and installation conditions. It also includes correction factors for ambient temperature and the number of current-carrying conductors in a raceway or cable. Fifthly, National Electrical Code, or NEC, Table 310.15b16 allowable ampacities of insulated conductors rated up to and including 2000 volts in raceway or cable or direct buried, based on ambient temperature of 30 degrees Celsius 86 degrees Fahrenheit. This table is the primary reference for determining the allowable ampacity of conductors. It lists ampacities for various conductor sizes and insulation types, such as THHN, based on the temperature rating of the conductor and the installation method. Sixthly, National Electrical Code, or NEC, Table 430.250 Full Load Current, 3-phase alternating current motors. This table provides the full load ampacity, or FLA, values for 3-phase alternating current motors based on horsepower and voltage. For example, a 1 horsepower, 480 volt, 3-phase motor has a full load ampacity, or FLA, of approximately 1.56 amps. Seventhly, National Electrical Code, or NEC, Section 250.122 Size of equipment grounding conductors. This section specifies the minimum size of equipment grounding conductors, or EGs, based on the rating of the overcurrent protective device in the circuit. The equipment grounding conductor, or EG, must be sized according to National Electrical Code, or NEC, Table 250.122. Eighthly, National Electrical Code, or NEC, Section 110.14c Electrical Connections. This section requires that electrical connections be made in a way that ensures a good electrical contact without damaging the conductors or terminals. It also addresses the temperature limitations of conductors and equipment terminals. Ninthly, National Electrical Code, or NEC, Section 250.45 Grounding of electrical equipment. This section requires that all electrical equipment be grounded to ensure a low impedance path for fault current. This helps to protect personnel and equipment from electrical shock and fire hazards. Tenthly, National Electrical Code, or NEC, Section 300.3 Conductors. This section addresses the requirements for conductors installed in raceways or cables, including the need to have all conductors of the same circuit in the same raceway or cable. Now, let's consider the specifics of the 480-volt motor installation. Firstly, voltage and horsepower. There are 18 1-horsepower, 480-volt direct drive fan motors. Secondly, control. 9 motors start from one selector switch energizing a square DIAC Elkhorn D32 amp contactor. Thirdly, motor protection. Each motor is protected by a square DGV2M7 motor protection circuit breaker, or MPCD, with GV2 G554 busbar. Fourthly, wiring from motor protection circuit breaker, or MPCD, to disconnect. Number 10 American wire gauge, or AUG. THHN conductors run from the GV2s to non-fused disconnects at each motor with number 12 American wire gauge, or AUG. THHN conductors and number 12 American wire gauge, or AUG, equipment grounding conductor, or EG. Fifthly, main breaker. The main breaker is a 40 amp I-line circuit breaker. Sixthly, feeder conductors. Parallel number 8 American wire gauge, or AUG, wires, with 3 conductors per phase, run from the main breaker to each 32 amp contactor. Now, let's address the potential issues. Firstly, undersized feeder conductors. The parallel number 8 American wire gauge, or AUG, THHN wires from the main breaker to the contactors may be undersized for the 32 amp contactor rating. Secondly, undersized tap conductors. The number 10 American wire gauge, or AUG, THHN taps from the number 8 American wire gauge, or AUG, branch conductors to each contactor are also undersized. Now, let's propose a solution. Firstly, increase the main breaker size. Replace the 40 amp main breaker with a 60 amp breaker to accommodate the total load and potential surge current. Secondly, upgrade feeder conductors. Run number 8 American wire gauge, or AUG, THHN branch circuit conductors from the main breaker to each contactor, eliminating the need for tap conductors. Thirdly, direct connection. Connect each contactor directly to the branch circuit conductor without any taps. Fourthly, verify motor protection circuit breaker, or MPCD, settings. Ensure that the motor protection circuit breaker, or MPCD, settings are properly adjusted for the 1-horsepower, 480-volt motors to provide adequate overload protection. Fifthly, grounding. Ensure that the equipment grounding conductors, or EGs, are properly sized and installed according to the National Electrical Code, or NEC, Table 250.122. In summary, by addressing the issues of undersized conductors and ensuring proper overcurrent protection and grounding, the installation can be brought into compliance with the National Electrical Code, or NEC, and provide a safe and reliable power supply for the fan motors. Let's talk about using the correct wire size based on ampacity. Firstly, determine the load. Calculate the total load in amps that the conductor will carry. This includes the continuous load, which is the load that operates for 3 hours or more at a time, and any non-continuous loads. Secondly, apply National Electrical Code, or NEC, Section 210.19 for branch circuits or 215.2 for feeders. These sections require that the conductors be sized to carry not less than 125% of the continuous load plus 100% of the non-continuous load. Thirdly, select the conductor insulation type. Choose the appropriate conductor insulation type based on the application and environmental conditions. Common insulation types include THHN, THWN, and XHHW. Each insulation type has a different temperature rating, which affects its ampacity. Fourthly, use National Electrical Code, or NEC, Table 310.15b16. Refer to this table to determine the allowable ampacity of the conductor based on its insulation type, size, and temperature rating. The table lists ampacities for conductors installed in raceways, cables, and direct buried applications. Fifthly, apply correction factors. If the ambient temperature is higher than 30 degrees Celsius, which is 86 degrees Fahrenheit, or if there are more than 3 current-carrying conductors in a raceway or cable, you must apply correction factors to the allowable ampacity of the conductor. These factors reduce the ampacity to prevent overheating. Sixthly, account for voltage drop. Calculate the voltage drop in the conductor to ensure that it does not exceed the recommended limits. The National Electrical Code, or NEC, recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. If the voltage drop is too high, you may need to increase the conductor size. Seventhly, consider termination temperature. Check the temperature rating of the equipment terminals to ensure that the conductor's temperature rating is compatible. Conductors must be sized based on the lowest temperature rating of any connected terminal. Eighthly, select the appropriate conductor size. Based on the calculated ampacity, correction factors, voltage drop, and termination temperature, select the appropriate conductor size from National Electrical Code, or NEC, Table 310.15b16. The conductor size must be large enough to carry the load current without exceeding its allowable ampacity. Ninthly, verify compliance. Ensure that the selected conductor size complies with all applicable requirements of the National Electrical Code, or NEC, and any other applicable codes or standards. Remember, when dealing with electrical installations, always prioritize safety. If you're not comfortable working with electricity, it's best to consult with a qualified electrician. Also, it is essential to consult the latest edition of the National Electrical Code, or NEC, and any local amendments to ensure compliance with the most current requirements. Now, let's review the key steps to ensure proper overcurrent protection for motor circuits. Firstly, determine the motor full load amps, or FLA. Obtain the motor's full load ampacity, or FLA, from the motor nameplate or National Electrical Code, or NEC, tables 430.248, 430.249, or 430.250. This is the starting point for sizing overcurrent protection devices. Secondly, select motor overload protection. Choose the appropriate motor overload protection device, such as thermal overloads, electronic overloads, or motor protection circuit breakers, or MPCBs. The overload protection device should be sized to protect the motor against overloads and failure to start. Thirdly, determine overload protection size. Size the overload protection device based on the motor's full load ampacity, or FLA, and the type of motor. The National Electrical Code, or NEC, Section 430.32 provides guidelines for sizing overload protection devices, which are typically set at 125% of the motor's full load ampacity, or FLA, for standard motors. Fourthly, select short circuit and ground fault protection. Choose a short circuit and ground fault protection device, such as fuses or circuit breakers, to protect the motor branch circuit conductors, control apparatus, and the motor itself against short circuits and ground faults. Fifthly, determine short circuit protection size. Size the short circuit and ground fault protection device based on the motor's full load ampacity, or FLA, and the type of motor. The National Electrical Code, or NEC section 430.52 provides guidelines for selecting the maximum rating or setting of the overcurrent protected device, which can range from 150% to 250% of the motor's full load ampacity or floor, depending on the type of protected device. Sixthly, coordinate overload and short circuit protection. Ensure that the overload protection device and the short circuit and ground fault protection device are coordinated to provide the best possible protection for the motor and the motor circuit. The overload protection device should trip before the short circuit protection device in the event of an overload, while the short circuit protection device should trip quickly in the event of a short circuit or ground fault. Seventhly, consider National Electrical Code, or NEC, requirements. Comply with all applicable requirements of the National Electrical Code, or NEC, for motor overcurrent protection, including the requirements for conductor sizing, overcurrent protection device selection, and coordination of protection devices. Eighthly, install and test protection devices. Install the overload protection device and the short circuit and ground fault protection device in accordance with the manufacturer's instructions and the National Electrical Code, or NEC. Test the protection devices to ensure that they are functioning properly and providing adequate protection for the motor and the motor circuit. Ninthly, document protection scheme. Document the motor overcurrent protection scheme, including the type, size, and settings of the overload protection device and the short circuit and ground fault protection device. Keep this documentation readily available for future reference. Tenthly, maintain protection devices. Regularly inspect and maintain the motor overcurrent protection devices to ensure that they are in good working condition and providing adequate protection for the motor and the motor circuit. This includes checking the settings of the overload protection device, testing the operation of the short circuit protection device, and replacing any damaged or defective devices. Remember, proper overcurrent protection is essential for the safe and reliable operation of motor circuits. By following these steps and complying with the National Electrical Code, or NEC, you can ensure that your motor circuits are adequately protected against overloads, short circuits, and ground faults. Now let's explore the significance of grounding and bonding in electrical systems. Firstly, grounding. Grounding is the process of connecting electrical equipment and circuits to the earth, providing a low impedance path for fault current to flow back to the source. Grounding helps to protect personnel from electrical shock and to prevent damage to equipment in the event of a ground fault. Secondly, bonding. Bonding is the process of connecting metallic parts of an electrical system together to create an electrically conductive path. Bonding helps to equalize the voltage potential between different parts of the system, reducing the risk of electrical shock and fire hazards. Thirdly, equipment grounding conductor, or EG. The equipment grounding conductor, or EG, is a conductor that connects the non-current carrying metallic parts of electrical equipment to the grounding system. The equipment grounding conductor, or EG, provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to quickly clear the fault. Fourthly, grounding electrode conductor, or GEC. The grounding electrode conductor, or GEC, is a conductor that connects the grounding electrode to the grounding system. The grounding electrode conductor, or GEC, provides a connection to the earth, helping to stabilize the voltage potential of the electrical system. Fifthly, grounding electrode. The grounding electrode is a conductive rod, plate, or other object that is buried in the earth and connected to the grounding electrode conductor, or GEC. The grounding electrode provides a connection to the earth, helping to stabilize the voltage potential of the electrical system. Sixthly, system grounding. System grounding is the process of grounding the neutral conductor of an electrical system. System grounding helps to limit the voltage to ground during normal operation and to provide a low impedance path for fault current to flow back to the source in the event of a ground fault. Seventhly, equipment grounding. Equipment grounding is the process of grounding the non-current carrying metallic parts of electrical equipment. Equipment grounding helps to protect personnel from electrical shock and to prevent damage to equipment in the event of a ground fault. Eighthly, bonding jumpers. Bonding jumpers are conductors that connect different parts of the electrical system together to create an electrically conductive path. Bonding jumpers help to equalize the voltage potential between different parts of the system, reducing the risk of electrical shock and fire hazards. Ninthly, National Electrical Code, or NEC, Article 250. National Electrical Code, or NEC, Article 250 provides comprehensive requirements for grounding and bonding of electrical systems. This article covers topics such as grounding electrodes, grounding electrode conductors, equipment grounding conductors, bonding jumpers, and system grounding. Tenthly, benefits of grounding and bonding. Grounding and bonding provide several benefits, including protecting personnel from electrical shock, preventing damage to equipment, reducing the risk of fire hazards, and improving the reliability of electrical systems. In summary, grounding and bonding are essential components of electrical systems. By providing a low impedance path for fault current and equalizing voltage potential, grounding and bonding help to protect personnel from electrical shock, prevent damage to equipment, and reduce the risk of fire hazards. It is important to comply with all applicable requirements of the National Electrical Code, or NEC, and to ensure that grounding and bonding systems are properly installed and maintained. Let's delve into the topic of conductor derating. Firstly, definition. Conductor derating is the process of reducing the allowable ampacity of a conductor to account for factors such as high ambient temperature, multiple current carrying conductors in a raceway or a cable, and other conditions that can cause the conductor to overheat. Secondly, ambient temperature. High ambient temperatures can cause conductors to overheat, reducing their ability to carry current safely. The National Electrical Code, or NEC, requires that the allowable ampacity of conductors be reduced when the ambient temperature exceeds 30 degrees Celsius, which is 86 degrees Fahrenheit. Thirdly, number of conductors. When multiple current-carrying conductors are installed in a raceway or cable, the heat generated by each conductor can cause the other conductors to overheat. The National Electrical Code, or NEC, requires that the allowable ampacity of conductors be reduced when there are more than 3 current-carrying conductors in a raceway or cable. Fourthly, derating factors. Derating factors are used to calculate the amount by which the allowable ampacity of a conductor must be reduced. These factors are based on the ambient temperature, the number of current-carrying conductors, and other conditions that can affect the conductor's temperature. Fifthly, National Electrical Code, or NEC, Table 310.15b3. National Electrical Code, or NEC, Table 310.15b3 provides adjustment factors for ambient temperature. This table lists the adjustment factors that must be applied to the allowable ampacity of conductors when the ambient temperature exceeds 30 degrees Celsius, which is 86 degrees Fahrenheit. Sixthly, National Electrical Code, or NEC, Table 310.15b3. National Electrical Code, or NEC, Table 310.15b3 provides adjustment factors for the number of current-carrying conductors in a raceway or cable. This table lists the adjustment factors that must be applied to the allowable ampacity of conductors when there are more than 3 current-carrying conductors in a raceway or cable. Seventhly, calculation of derated ampacity. To calculate the derated ampacity of a conductor, you must multiply the allowable ampacity of the conductor by the appropriate derating factors. A derated ampacity is the maximum amount of current that the conductor can safely carry under the given conditions. Eighthly, National Electrical Code, or NEC compliant. It is important to comply with all applicable requirements of the National Electrical Code, or NEC, for conductor derating. Failure to properly derate conductors can result in overheating, insulation damage, and fire hazards. Ninthly, examples of derating. Examples of situations where conductor derating may be required include conductors installed in hot environments, conductors installed in crowded raceways, and conductors installed in underground conduits. Tenthly, importance of derating. Conductor derating is an important safety measure that helps to prevent overheating and fire hazards. By properly derating conductors, you can ensure that they are able to carry the load current safely and reliably. In summary, conductor derating is the process of reducing the allowable ampacity of a conductor to account for factors such as high ambient temperature and multiple current carrying conductors. It is important to comply with all applicable requirements of the National Electrical Code, or NEC, for conductor rating and to ensure that conductors are able to carry the load current safely and reliably.